Welcome everyone, thank you for being here. My name is Lars Moormann, and today I'll give you a presentation about the research I've been doing here for my internship. And it's about parallel programming using discrete event systems. So just a small introduction to myself. Wait, how does it work?
Yes.
I don't know, I just picked it up, but
Can you catch?
if you throw it well.
I almost trying to get in the cup. Take one of the things on the side, on your left side. Take on the left. Yeah, take that thing and put the one I gave you in there.
Well planned.
Yeah. Let's see if that works.
Alright. Try again. There we go. Okay, well, like we said, I'm from the Netherlands. It's my international internship, so it's like a 3-month research. Now my thesis comes after this. Most people know Amsterdam, which is why I put it there, but I'm actually all the way from the south, called Amsterdam. But for my study, I moved to Eindhoven, which is where my university is at.
Eindhoven is a great university, man.
Probably, yeah. It's a technical university of Eindhoven where I study mechanical engineering. And part of the mechanical engineering study was discrete event systems, which is how I got into this research. I'm not sure how many people know about discrete event systems, so that's why I decided to do like a small introduction to it so that people know the basics. So discrete event systems are basically made up out of models like these, like a couple of them. This is just a basic example. And they're made up out of states and events. And the states are the circles you see, and the events are the arrows connecting them. And in this case, I'm modeling a machine. The machine has 3 simple states that can be off or on, and it can break down, which makes it go to the broken state. And the events are pretty self-explanatory. You turn it on, you turn it off, and if it's on, it can break down when we have to repair it. Okay, the off state has 2 circles, which indicates that it's the initial state. So we assume that it starts off in the off state. Then there's also a different type of state, which is the marked state. And marked states basically indicate our desired state. So these are the states we want the system to be in. In this case, I assumed we either want to have the machine be on or off. We don't want the machine to be broken, so that's why it's not a marked state. Okay, this is the thing for the states. We also have 2 types of events. Basically, they're uncontrollable or controllable events. And the name is pretty self-explanatory. Controllable events are the events that the system can decide happen, while uncontrollable events are events that can happen at random. And in this case, well, the system can decide to turn on the machine or turn off the machine, but if it breaks down, well, that's uncontrollable, so that's why it's an uncontrollable event. And we indicate this by the exclamation mark in front of the breakdown event. Okay, so this is only one part of a discrete event system. It's usually made up of a lot of these. And every part is either part of the plant or part of the supervisor. And I'll start with the plant. The plant is basically all possible behavior. So in this case, my example has 2 machines. It's the same machines as before. And it covers all possible behavior, so all the states it can be in, whatever. Then we add supervisors to basically impose rules on this system. So we want desired behavior, and in my example, I decided that the rule is that the machines cannot be on at the same time. So we only want one machine running at the same time, which is why we add the second model. And in this case, we start in an off-off state, which basically indicates that both machines are off. We can turn on either one of them, but before we can turn on the other one, we first have to turn off the first one. So you end up with your desired behavior, which is only one machine on at the same time. And that's the supervisor. It's more like a virtual added rule to the system. Now there are 2 main properties to a discrete event system, which basically, well, tell you something about the system. And the first one is called non-blocking. And non-blocking indicates if your system can always get back to a marked state. And again, the marked states are the black states. So if there's always a possible set of events to get back your marked state, then your system is non-blocking. And the second property is controllability. And controllability basically says that if your plant says that an uncontrollable event should be possible, so in this case the breakdown event, then our supervisor can never prevent that from happening, because it's uncontrollable. So we cannot impose rules preventing that from happening. So as long as that's the case, our system is controllable. These are the 2 properties that will be mentioned later on. These are important. Okay, that's my basic explanation of discrete event systems. For my research, I applied them to parallel programming. And the way I use them is basically to verify if we have a piece of sequential code, as we see over here, and we have a way this code is parallelized. So in this case, we have two branches in which we put the lines of code. So we parallelized it, and we want to verify if this is a good way of parallelizing it. There's like good ways and wrong ways. If the correct results come out, then it's a good way, and we want to verify that using discrete event systems. And the first part of that is modeling the plant. And once again, the plant has to cover all possible behavior. So for the sequential piece of code, possible behavior basically means line execution. All the lines need to be executed at some point, but we don't really care about the order just yet, because it's possible behavior, all possible orders. And the way I did every line is basically by a model like this. It's very simple. We start with a controllable event, which is an initiation event, and afterwards comes an uncontrollable event, which is the actual execution. And this is an example for the line with the arrow. Oh, you can see the arrow. And all of the lines, except for the initiation events, have a model like this. Then the second part is part of the supervisor. So these are the rules to the system. And the rules for this system are the dependencies between lines. So in this case, I have the example of the two lines with the arrows. As you can probably see, the second line depends on the first line because it has the same variable. So we create a dependency saying the first line needs to be executed before the second line. It's very straightforward. That's the second part of the modeling. And then there's the third part, which is a bit more complicated. This is connected to the parallel section. In this case, we have two branches, which also make us also have two different models. It looks complicated, but it's actually very simple. We basically go through all the lines in the section. Let's say the first one is C1, C4 is C1, and that's the top model. So we basically first initiate ourselves, which is a self loop. Then we execute it. Then we do the next line, we execute it until we get through the whole system and end up in a marked state. And we create a model like this for all parallel branches. Okay, that's the modeling I did. But now we want to see if it actually works as intended to find incorrect parallel models. And to do this, we take all the models I just created, we import them into a program called Despot, and Despot tells us the system properties, which I explained earlier, the non-blockingness and the controllability. So there are two possible ways to make an error in parallel programming, at least two main ways. And one of them is if you have two dependent lines of code, they have a correct ordering and they have an incorrect ordering. Well, if you implement incorrect ordering, we want the system properties to indicate that we made a mistake. So in this case, I purposely made a mistake because, of course, you can see the top one has an incorrect ordering. I modeled this, imported it into Despot, and as it turns out, the system in this case became blocking and uncontrollable, which is good because this indicates that we indeed found the error. There's also a second error you can make in parallel programming. Once again, we have two lines of code that are dependent on each other, but we place them in two different branches. Now, if two lines of code are in two different branches, we cannot guarantee that they are executed in the correct order because the order is arbitrary. So once again, we want to find this type of error by using the system properties. So we parallelize them in a different way, making the different error, imported everything to the Despot, and in this case the system became uncontrollable, which once again is good because we found the error we made. Okay, well, that's the first part of my research, but to keep things fairly simple and within time and everything, I decided to only globally tell you what else I did instead of going into detail for everything because it would get tedious. So the second part of my research was basically focused on all the modeling I did up to now was manual and took a lot of time. So I basically created a program in C++ that uses the sequential code and the parallel code as input and parses them, and then automatically finds all the dependencies and write statements, and then the program outputs the discrete event system files, so the models. So this basically has two advantages. It's no more manual work, so if you have a big piece of code, it would take a couple of hours of modeling. In this case, it takes less than a second. And you can do much more complex codes because since it's automatic, well, no errors will be made. Even, well, if you do everything by hand, you'll probably make some mistakes and you have to do it again. So that's the two main benefits of this. Yeah, that's the second part of my research. And there's also a third part, which moves on from just a verification step. Up to now, it was only, we always had a sequential part of code, piece of code, and the parallel piece of code, and we wanted to verify if they were correct. in this part of my research, I only had the sequential piece of code, which was again imported into a C++ program. It parsed it again, found all the dependencies, and then the program actually did the parallelization. So the program divided all the lines into separate branches, which is the optimum way of doing it. And so the program tells us what would be the good way of parallelization, making parallel. And as well, your question?
So for that step, are the DES files and the parallel code generated separately, or are you generating the DES files first and then using those to create a parallel version?
Right now it only creates the DS files, and from that you can get the parallel code, but it's also possible to write it to a separate parallel file. But
and then in terms of the sequential code that comes in, like you're taking into account like loops and
yeah, it's like I introduced some like basic functions like for loops, while loops, if statements, arrays, but I kept it reasonably simple to make my program be able to run it. Like yeah, so to a certain degree it supports things like that. So yeah, the main benefit from this part is that it's more than just verification. It actually has a purpose, the program, which is a lot more useful in practice. Well, that's basically all I did for my research. I want to thank you for listening. This ends my presentation, and if you have any questions, please ask them.
So there's a separate DES model for every thread that's involved in parallel code, right? Are there any, or do you run into any issues when there are many threads versus just a few threads? For example, the examples you've shown, you've only given us examples of 2 threads.
No, you can do as many as you want. And in my example, it was actually a fairly simple example because we have 2 threads which are fully parallelized.
Yeah.
But mine actually supports every combination of threads. You can have like one start and then it splits up and then it comes back again and splits up and whatever you want.
Do you do any load balancing in terms of the number of threads that are involved to ensure that the equal number of work is being done by every thread, or
it doesn't really go that much into detail. It's just we parallelized it beforehand, hoping it's a good way, and then the system checks if it's actually giving the correct results.
So there must be some kind of work distribution involved, right? For example, if you have 2 threads versus 5 threads, you must determine how many lines of code each thread will execute, right?
Well, we do the parallelization.
Okay.
So that should be done beforehand. I mean,
but the third part.
Yeah. Okay. Yeah. That one only splits it up into separate branches up till now. So it's
right. But the splitting up the separate branches, you're putting.
We try to put everything in as much branches as we can, which would be the optimal way. I mean,
right.
If you have more branches, it means you have more parallel branches, which means it's faster. Okay.
If you have a parallel program that uses like LICS, is it able to detect those and say it's still okay?
LICS?
Like mutex?
Yeah, mutex is the right one type of thing.
Or like semaphores? You know?
I guess I know what a mutex is. Like, it's like the initiation of the.
It's like
basically a shared resource between 2 threads.
Yeah.
Okay.
One
yeah, we have like I assume that it's like a shared memory. So if something happens in one thread, it happens in the other thread as well. So you want to, if 2 variables are dependent on each other, you want them in the same thread because you cannot guarantee correct ordering if there are multiple threads. So it's not really use of mutex.
Lars' example, he gave me an example earlier where anything that kind of affects one variable is just put in the same thread.
yeah.
Actually, following on that question, if your initial sequential code is purely sequential, how will your program handle that? Can your program
Purely?
handle that?
So it cannot be split in any way?
Right.
Then it will be output in the same branch and we'll end up with the same code as you had.
I leave for a minute and this what happens? Like,
Whoa.
I didn't know.
More than a minute, but yeah.
That's very easy. It was just like, show me the last 2 slides. Like, I went to get a knife.
I'll send you them. It should be on tape, so you can.
All right. Like, I didn't have a dagger because there's rules against that. All right. Well, thank you for presenting, Lars. Thank you. Stay there. I'm gonna stand down.
Yeah, he's serious.